This is 9.2 day 1, the law of sines. So what we're going to be looking at today are triangles that are not right triangles. And what are you going to do to find their missing sides and their missing angles? If they're not right triangles, you're not going to be able to use Pythagorean theorem. Triangles that don't have any right angles at all are called oblique triangles. So what you see in A and B are two examples of triangles that are not right triangles. The first one is where all three angles inside of the triangle are acute, and the second picture shows you one angle being obtuse and the other two angles would have to be acute. When we calculate missing sides and missing angles in oblique triangles, we don't actually use Pythagorean theorem. We do some other calculations that are algebraic. An oblique triangle has a set of ratios that you can create that can actually be set up as proportions. What we're going to do right now is discover how we can come up with those ratios and then derive the proportion for it. Alright, so what we're going to take a look at is the triangle that's over on the right hand side, and what we're going to do is create a scenario that does have right triangles in it. So what I'm going to do is start with drawing an altitude from angle B to side B. So go ahead and take your pencil and you can do the same thing. So I'm going to extend this straight down like that, and then I'm going to go ahead and add in my right angle markings. You can put one or you can put them on both sides. So that's an altitude where I've drawn from vertex B to side B using a perpendicular. So this says, what is the ratio for sine A? Well, I'm going to go ahead and label this altitude H. And if I do a calculation for sine A, I'm going to think about SOHCAHTOA. So I've got SOHCAHTOA, I'm going to write it up here. So SOH, which is sine is opposite over hypotenuse. Cosine, well, we really don't need to write out the cosine because of the fact that we're only focusing on the sine ratio. So the sine of angle A is the opposite, which is h, over the hypotenuse, which is little c. So little h, little c. And I do want you to notice that in this picture, the angles are indicated with capital letters, and then the sides opposite them are listed as their lowercase letters. Now it says, what is the ratio for the sine of angle C? So angle C, so we have sine of angle C, and its opposite is also an h, and it's over the hypotenuse, which is little a. So I'm going to solve both of these ratios for h. So if I take this first example here, I can go ahead and solve by h by multiplying both sides by c. So I'm going to go ahead and show this one really quickly. So sine A equals h over c, and we're multiplying both sides by little c, and you'll get that h equals c times sine A. And make sure you're clear that that's the little c. So little c, and then the sine of big A. If I do the same thing and solve for h for the sine ratio for sine C, I get h equals little a times the sine of big C. So now what I'm going to do is use substitution and combine those two equations together. So I'm going to rewrite them. And I'm going to go ahead and use substitution. I notice they're both equal to h, so I can actually take both of the right-hand sides and set them equal to each other. So I have little c sine big A is equal to little a sine of big C. So now all I have here are each of my representations for sine of an angle as well as its opposite side. So what I'm going to do is I'm going to make sure that I have all the a's on the same side. So I'm going to divide by little a on both sides, which is the length. And of course the a's will cancel out. But I'm also going to move the c's to the same side. So I'm going to take little c and divide both sides by that value. So the little c's on the left side cancel out. So what I have is that the angle sine value divided by its corresponding side little a is equal to the sine of angle C over its corresponding little side. Now, I could go on and redo an altitude. I could add another altitude into this picture to calculate a B equivalency, but for time's sake, we're not going to do that. We're going to go ahead and just add this assumption in, that the sine of angle B over its corresponding side, little b, will be equivalent to all three, or all these other ratios as well. What you just showed with these proportions is called the law of sines, that if you have any type of an oblique triangle, you can create proportions of the sides and their matching corresponding angles in terms of their sine ratios. So in order to do this, you're going to need to know a couple situations. This first one over here for today, as long as we know two angles and one side, we'll be able to use the law of sines. Now tomorrow, we're going to be taking a look at situations where we have one angle given and two sides. It is important to note that because of the fact that you have three values in this extended proportion, what I can do is separate them out. And that's what I have here. And you don't have to take notes on this part. We'll do this in the sample problems. But you actually only work with two of these ratios at a time. So you can see right here, this first scenario is just these first two set equal to each other. The middle is the first and last ratio set equal to each other. And then this last proportion is the second and third ratio set equal to each other. And of course, another thing to keep in mind as we move forward is simply that the three angles together have to have a sum of 180 degrees. A couple things to remember. So just briefly repeating what I had mentioned. In order to use the law of sines, you're going to need to know three parts of this triangle. You're going to need to know two angles and one side. And that's for today. And those are called, whoops, there we go. We can call that angle, side angle, or side angle, angle. This side angle, angle may look familiar to you. We called it angle, angle, side in geometry, but they generally in your textbook call it side angle, angle. So that's what we're focusing on today, just two angles and one side. Now tomorrow in the next lesson we'll be looking at scenarios that use law of sines where you have one angle and two sides. There is a scenario you cannot use law of sines, and that's where you have three sides. You're not allowed to use that. So what we can do here is say that you can't use it if you know side, side, side. So we'll be using what's called the law of cosines for that. So once again, let's go ahead and recall a few things from geometry that we might need to know. And let me switch gears here. So first thing is that the sum of the angles of a triangle have to be 180. In order to actually create a triangle, any two sides, their sum must be greater than the third side. And then of course there's the logic of sides. The longest side is opposite the largest angle. The shortest side is opposite the smallest angle. Now from the unit circle and working with sine inverse, we know that the sine of an angle, the ratio itself, cannot be bigger than 1. If that occurs, you don't actually have a triangle. And the last thing that might be helpful for you, base angles in an isosceles triangle are equal or congruent. That may come in handy with one of your practice problems. So our first practice problem, it says solve the triangle where A is 40, B is 60, and A is 4. So you're going to want to do a rough sketch of this, and it doesn't have to be perfect. Do the best you can with your drawing there. A little bit crooked on my part. So we have A, B, and C, and they tell us that angle A is 40 degrees, and we know that angle B is 60 degrees. And we know side A is corresponding to angle A, it's opposite from it, and we have a 4. Now it says solve the triangle. When they say solve the triangle, that means find all missing angles and sides. Find all missing angles and sides. Before we even get started, make sure that your calculator is in degrees. So go ahead and change your mode before you even start the problem. Okay, so we know that we have 3 angles and we have 3 sides. So I'm going to go ahead and write the capital letters to represent the angles, and the lowercase letters will represent each of the sides. And then I'll fill in what I already know or what is logical. So we know A is 40, B is 60. Those are in degrees. And it is logical to calculate angle C. I know that there's 180 degrees in the triangle, so I'm going to take 180 minus the other 2 angles, which is 100, to give me an 80-degree third angle. And then, of course, I do not know side A, or I do know side A, sorry about that, that's a 4, but I do not know side B and C. So what I'm going to do is write down the proportions, all 3 of them that are represented in the picture. So let's go ahead and do that. So starting with A, so I have sine of 40 degrees over its corresponding side of 4 is equal to the sine of 60 over the side B that corresponds to it. And then we've got our angle C, which is the sine of 80 over the corresponding side C. You'll notice that the 3 ratios, the only one that actually has both the numerator and denominator as a physical value is the sine for the ratios of A. So we're going to actually set that one equal to both of the other 2 ratios separately. So I'm going to go ahead and split that up and make those 2 proportions. So we've got sine 40 over 4 equals sine 60 over B. And the second one we have sine 40 over 4 and sine 80 over C. Now I have seen lots of examples where people go ahead and put in the decimals right away for sine 40 and sine 60, but I think it's easier just to round once at the very end of the problem. So I'm going to go ahead and do proportions for this and do some cross multiplication. So if I'm solving for B, what I'm doing is multiplying 4 and sine 60, and ultimately I'll divide by sine 40. So I'm going to go ahead and streamline this and just go ahead and write it in that format. So B is going to be equal to the 4 times the sine of 60 over the sine of 40. And over here on the other side, I'm going to have that C equals 4 sine 80 over sine 40. Go ahead and put both of these into your calculator. And this first one, so you're going to do 4 times sine 60 divided by sine 40. And what I'd like you to do is round to the nearest hundredth. Sometimes the textbook will tell you to round to the nearest tenth. In this case, just to be safe, let's go ahead and go to the nearest hundredth, so 5.39. So I'm using an approximation here because I know that I'm doing some rounding. So I'm filling in letter B here, and that's going to be approximately 5.39. And then go ahead and put the C value into your calculator, and you're going to get C is approximately 6.13. Now before we leave this problem, it is a good idea to double check that you actually have a triangle. If I add the lengths of side A and side B, I can see that they're over the value of 9, which is bigger than the 6. And if I add 6 and 5, those add up to 11. And they're, of course, bigger than the 4. And then if I add the 4 and the 6 together, they're bigger than the 5. So I'm checking to make sure that I actually have a triangle by verifying that any 2 sides are larger than the third side. And I don't need to be exact with that. I can do an approximation. Example 2. Let's go ahead and do this one. Now this is an example of an angle, side angle, where the side is in between the 2 values. So we're going to go ahead and draw another triangle. And now this one is going to have an acute angle, or 2 acute angles and an obtuse angle somewhere. So I'm going to go ahead and draw this one a little bit more of an accurate representation of what that would look like. So I know that angle A and angle B are going to be acute. And I know C is going to have to be obtuse because of the sum being 180 in the entire thing. So angle A is 35. Angle B is 15. And then side C is 5. So I'm going to go ahead and list out my capital letters for my angles, and then my lowercase letters for my sides, like that. And I've got the 35 and the 15. And logically, I know that angle C is going to be 180 minus 50, which is 130 degrees. So I could add that into my picture if I want to. And then I also know that the side across from angle C, which is the lowercase c, is a 5. So now I'm going to go ahead and write my extended proportion with all three ratios in it. So I have the sine of 35 over A equals the sine of 15 over little b equals the sine of 130 over 5. And notice the third ratio is the one that has both the numerator and denominator as physical values. So I'm going to go ahead and set the two proportions up that I need. So sine 35 over A is equal to sine 130 over 5. And then my second ratio, sorry, my second proportion, I should say, sine 15 over B equals sine 130 over 5. I'm going to go ahead and cross multiply, and I'm going to keep this quick. 5 times the sine 35 divided by sine 130. And over on this side, I'm going to have 5 sine 15 divided by sine 130. And go ahead and do your calculations on your calculator to get your approximations. So 5 sine 35 divided by sine 130 is approximately 3.74. And the second one, 5 sine 15 divided by sine 130 is about 1.69. So I'm going to go ahead and fill that in on the side over here. So once you have all 6 filled in, you know that you're finished. So we had to fill in C, A, and B. So once again, a quick reminder that you're filling in 3 of them and you initially know 3 values. The last 2 problems are practice problems. I'd like you to pause the video and work out each one separately, and then unpause the video and check each answer. Go ahead and check your work for number 1. Pause the video if you need to check through the steps. Workout number 2. Pause the video, and when you finish, check your answers. Go ahead and check your answers to number 2, and this concludes 9.2, day 1.